There it goes. Make sure my microphone's working. Yes, it is. Okay, so welcome everyone to Kopernik Observatory and Science Center this evening. We have clear skies tonight, so we are definitely going to do some observing. And that is, thankfully, the topic of tonight's show. Usually when we have programs about the night sky, we're always clouded out afterwards, so we can't show you the real sky. But we lucked out, and we have clear skies, so that's great. We also just wrapped up our family STEM hour. Many of you were there for that. That was in physics. The 3D Universe program goes on all October, except for October 15th for International Observe the Moon Night. There we're going to do lunar activities instead of the 3D Universe topic. But you're always welcome to come up to that. We usually do try and change it up from week to week, but it is the same topic. So again, this month's topic is on 3D experiences, so using 3D glasses to look at the night sky, or space in general. So, of course, if you want to learn more at Kopernik, I'm going to switch my view here. There we go. You can go to kopernik.org for more information about our upcoming programs. So, like I said, Family Hour is going to be reported here. This month is 3D Universe. Next month is hovercrafts. So you actually get to build your own little hovercraft. Take it home. We'll talk about how hovercrafts work. That one is for November. Always begins at 7 p.m. Then tonight's program is Fall Skies, but you can, of course, go up to public programs and upcoming Friday nights to see more. So we have our whole fall list here. So feel free to explore. We also have paper copies out in the lobby. So you're welcome to take those home too. Okay, so next month, for example, is from Director of Clean Energy Programs, Adam Flint, about energy systems of the future, particularly building energy systems. Okay. What else do I want to... classes, too. We have Girl Power registration happening now for November, so you can check that out on our site. With all our class programs, we offer online registration, so feel free to utilize that. We also do have paper forms in the lobby. And, of course, you can find summer camps or any after-school programs we may end up doing in the future. Those will all be listed here. Kopernik Kids, too. That's one other thing we're running right now. I'm not sure if this month's class is full, but we do have a spooky science class for ages 3 to 6 on October 16th. All right. So there's a couple other things on our website I'll show you during the program that have to do with astronomy. Last thing, what we're doing right now, and you can see it right here, we are streaming this program to our YouTube channel too. So if there's ever a night where you can't come up to Kopernik, not only do we live stream it, but it does record to our channel as well, so you can always go back and watch it on another day. And we have a variety of stuff too, from observing live streams, like one of the cool things we did. Why doesn't it want me to scroll? Maybe I'll refresh the page here. There we go. Like I said, we have all our backlog of shows here. We also have observing live streams. So we actually looked at like Comet Neowise, live views of Mars and the other planets. And the cool thing is the solar system's dynamic, so all those are very different experiences. So feel free to check us out there or subscribe to the channel and keep up to date on our virtual side of Kopernik. Okay, let's get into the main program here, which is the fall skies and also a lunar eclipse preview. There is a lunar eclipse coming up. I will say don't get your hopes up too much for it because it's not a convenient one. So my name is Jeremy Carty. I am an educator and a coordinator here at Kopernik. During the virtual programs we've been running, I've sort of taken on the role of our live stream astronomer. I've run those observing live streams in the past, so you'd see me there if you ever tune into one of those. So that's my background is in physics, and I'm also a graduate student in sustainable energy systems. And I've been at Kopernik for 10 years now, I think. And I've learned so much, and I'd like to share that with you now as in relation to fall skies and what you can see in autumn in the sky. All right. I'm going to use this clicker here if it'll work for me, because that will be a little more convenient, I think. So what we're going to discuss, we'll talk about the ABCs of stargazing. This actually came from a presentation by the Kopernik Astronomical Society, which is our astronomy club, effectively. We have a couple members in the audience from that club tonight. And I sort of took that because it was a really good way to describe some of the very basics of understanding how the night sky moves. So we'll go through that. What can we see in the sky? So tonight we're going to talk about the International Space Station. And little teases to what's to come. About halfway through, I set an alarm on my watch. About halfway through, we're going to break from in here and go outside to see the ISS with our eyes in the sky. We'll talk about what we're seeing when we're out there, but I do have some slides that I hope I can get to before that. So stay tuned, because we'll break and then we'll come back in here to wrap things up. All right, next up we have solar system objects and deep sky objects. So things within our solar system we can see in the sky, and deep sky is stuff outside of our solar system. All the dimmer objects, the stars, star clusters, galaxies, things like that. We'll talk about what's out there now. And then I have some observing tools for you that are incredibly accessible. Some of them are free too, and more than likely you already have one on you. At least one person in your family should have one on you. So we'll talk about the tools you can use for astronomy and observing. Okay. The ABCs of stargazing. A is for angular size and distance. Don't let that term scare you too much. We're just going to talk, it's a little bit mathematical, but it's talking about degrees. So if you've ever worked with angles before, or used, what's like a protractor for actually measuring angles from 0 degrees and then upwards to 90 degrees, then that's all we're really talking about here. Just an angular measurement. And you can use different, gestures on your hand to represent the different degrees in the sky. Now, what's important is your arm, when you're doing these motions, the 3 or the fist, or kind of like the Spider-Man, you make sure you have to have your arm all the way stretched out for this to work. You can't bend your elbow at all. It has to be all the way out to make these measurements work with the sky. Okay? So with just your pinky out, and you're holding it up to the sky, the tip of your finger there represents 1 degree, a 1 degree measurement across the sky. Then, with all 3 fingers out, nice and close though, holding them out to the sky, let's say you're trying to measure the distance between stars, 5 degrees. So if you have 2 stars 5 degrees apart, your fingers should fit right in between them. Still with me? Then we have your fist. That's the width of your fist is 10 degrees out, 10 degrees apart. And then you have the Spider-Man, or whatever you want to call it, your 2 fingers stretching out. That's 15 degrees apart. Then I think there's one more that's not listed on here. That's like the radical dude, surfer guy, right? That is 25 degrees apart. If you want to do your thumb and your pinky finger stretched all the way out, arm stretched out, that's 25 degrees. And one cool thing you can do, if you're trying to measure the altitude of an object in the sky, you can sort of do this motion, especially when you're dealing with your 2 fingers there. If you have your 2 fingers spread out like that, you can do like a twisting motion and count up. As long as you keep track of the pivot, right? Which finger you're pivoting around, you can get a rough idea of how high things are in the sky. This is a very loose and fast rule, but they give you an example there of the Big Dipper, and you can measure the distance between the stars there. So in the cup, the top two stars in the cup, right here and here, that's 10 degrees apart. So you can use your fist. You can try that out tonight with the Big Dipper. It should show up. And you can reach your arm out and measure 10 degrees apart. What's really cool about this, too, in the case of your pinky, the moon should fit within your pinky. It'll actually be a little bit smaller, believe it or not. And I'd like you to test that sometime, too. Test that with the moon near the horizon and with the moon all the way up in the sky at the highest point. Because you know how sometimes the moon looks like it's bigger when it's close to the ground? And then it gets smaller? That's just your brain. It's your brain doing that. Giving you sort of an optical illusion of giving you your reference to the ground. It makes it look like it'll be bigger. It's, again, optical illusion effect. And then when it's higher up in the sky, you have nothing to compare it to, so it looks small. Try that out with this method. See if it'll be the same size. All right, carry on here. That is A for angular size and distance, how we can measure where things are in the sky with degrees. Next is B for brightness, or we call this in astronomy magnitude. So how bright is an object in the sky? You know, the moon's very bright, right? The sun's super bright, but some of the stars are much dimmer. So we got to try and compare those things. And we have this nice little scale here to use. So on our scale, we have plus 25 to negative 25. And you can already tell this is not what we'd call intuitive. Because you see what it says at plus 25? Very faint. Negative 25, a very small number, right? Very bright. Okay, well, we got to keep that in mind. It's reversed of how you'd expect it to work. So, as an example, the sun is all the way on the other side. It's a negative number, about negative 27, if I remember correctly. That's a very bright object, but it's all the way on this side of the scale. So negative numbers are bright, positive numbers are dimmer. Okay, then we have the moon, another bright object, about negative 12, 13 or so. Venus, one of the brightest planets we can see. Maybe you've been seeing in the western sky as the sun sets, you've been seeing this bright object out there. Almost guaranteed, if it's not moving or anything, that's Venus. You've been spotting Venus in the sky. So keep an eye out for that one. It's going to get higher and higher as the fall goes on. Sirius, one of the brightest stars in the sky. It'll show up really nicely in the wintertime. Sirius is just below 0. Vega, a star that'll be out tonight for sure. Nice bright star. That's almost exactly 0. Then we get into the positive, the fainter stuff. Around 6 is the faintest naked eye star you can see. So when I say naked eye, that means you don't have a telescope, you don't have binoculars, you don't have a camera. It's just your eye. And you're looking up. The dimmest thing that you can see is at 6. That your eye can pick up in the sky. Okay? Brightest quasar. Quasars are actually end up being pretty dim objects. They're very violent objects in the universe, though. But brightest one that we can see is well past our vision capabilities. But with a telescope and camera systems, they can pick them up. And up here, when you get into 25 and 30, that's where the Hubble Space Telescope can operate. It can operate below that, too, with brighter objects, but it can also access very, very dim things. So our scopes can probably fit in between 15 to 20, like the 20-inch can get into that range, but it can't get anywhere near the Hubble Space Telescope. So the faintest objects are going to be way out here. So that's brightness. So when you see, we'll look at some software later called Stellarium that will show you the brightness of things, the number. And you can compare that to this chart and see if it's something you can spot with your eye. Now, of course, like I said, when you have instruments, you can see even more with those tools. All right. C. We're only doing ABC, by the way. We're not going through the full alphabet. So C is for coordinates. This is going to get us a little bit more familiar with the angular measurement, too, of the A. In fact, if I could, I probably would have switched these two, but ABC, right? So our coordinate system in the sky, the one that's best used in your case for observing objects in a given night, when things aren't changing too much, is to use this left side. We call this the alt-az. Altitude and azimuth. And that's, we have these people right in the center, right? And that's you, right? And then you have your coordinates all around you, your north, south, east, and west. And we measure this all in degrees. So north is going to be 0 degrees, east 90 degrees, south 180, west 270, and then back to 0. That's your azimuth. It's the circle on the ground, your imaginary circle surrounding you on the ground of your visible sky. Then we have to talk about altitude, because if we're just looking down at this circle, we can't see anything as we spin around. So we have to raise our heads up to see things in the sky, and that's your altitude. So that's going up in height to look at things in the sky. All right. Now, 90 degrees, it's like a right angle, right? 90 degrees is straight up. Objects that occupy that area of the sky, if you don't have a chair or you don't lie down, that can hurt to look straight up. So those objects you want to be lying down on the ground probably. But then it's just a full range, right? So 0 degrees to 90 degrees. And then you go back along the other side. That's your altitude. So that's how we can measure, and again, these degrees, the same hand gestures we were talking about before, right? Your pinky, that's 1 degree. So you can use those same measurements, the 3 fingers, is that 5 or 10? Now I forgot. But you can use those little tips I showed you before to make those measurements in the sky of where these objects are. Now there's another coordinate system astronomers tend to use, and our telescopes all utilize in the domes, and that is this crazy one we're seeing here. Do you see the Earth in the middle there? We call this sphere around the Earth the celestial sphere. Now it's not actually the way the space works. You know, if you extend out, it's just everything's so far away. We can have this sphere around us that represents the stars in the sky because they're not going to change much. The planets will move through this coordinate system. But otherwise, the stars and the constellations, they can stay put relative to each other. So, like, the Big Dipper relative to Polaris, those are always the same distance and in the same place in this sphere. It gets a little complicated, but the main thing is that the alt-az is our experience here on Earth. When we're on the surface of the Earth, we see objects moving across the sky, right? We see the sun rising and setting. We see the stars rising and setting, the planets, and so forth. This one's really good for our perspective when we're just observing on a given night. But if you want to talk about how objects are related to each other in this sphere, we have to use what's called right ascension and declination in that coordinate. So if we take the moon as an example, rising and setting across the sky, your alt-az is going to change. So at one point, the moon, as it's rising, is going to be just above 0 degrees in altitude. Later on, it's going to get higher in the sky. It might be 40 degrees up. That's changing throughout the night. Right ascension and declination is very specific, and you'll find that right ascension and declination don't change too much for the moon. And for stars, it doesn't change at all. The stars always have the same right ascension and declination. So this is a definitive way to coordinate in space and our view of the constellations in space, whereas alt-az is a more day-to-day. Where is this object right here and right now? Okay? So we'll probably use the left one if we do any measurements tonight. All right, there's your ABCs, a quick astronomy lesson of how we find things in the sky. There's a lot more to learn there. So what can we see in the sky? Keeping an eye on time. Around 8:30, we're going to go on a brief break outside. What can we see in the sky? Well, this is what we're going to see in the next 10 minutes or so. We can see the International Space Station. Now, before we started launching things into the sky, into orbit around the Earth, this is not something that humans ever saw, because these are artificial satellites. The moon is a natural satellite orbiting around the Earth. Then you have artificial satellites that we launched into space. And the International Space Station is one of them. It's a habitat in space where the astronauts go from across all nations that were part of this program. And there's 7 astronauts up there right now that we will see in a minute. But here it is, the ISS, and the Earth below it. So the ISS is in orbit around the Earth right now. That's why we're going to see it pass overhead, like I said, in the next 10 minutes. It orbits 250 miles above the surface of the Earth. It's actually a fairly low orbiting object. It's still within the atmosphere, but a very high up portion of the atmosphere where it's not going to slow it down too much. But every so often it slows down enough that they have to bump it back up and get it back up to speed to keep it going in around the Earth. Okay?
A second.
Yes.
It's sounding like a
Oh, too high, yep.
So try it again.
Yep, there we go. Maybe that's good. Yep, okay. So, oh, yeah, for the clicker. Okay, so, then the Earth. So it's 250 miles above the Earth. It orbits every 90 minutes. That's pretty quick, right? Our day takes 24 hours, but the ISS is going around the Earth every 90 minutes. It's a really quick orbit at a speed of 17,500 miles per hour. Now, someone asked, one of the students asked in the other room for the 3D universe, why doesn't it feel like we are moving here on Earth? We're rotating very quickly and we're orbiting around the sun. Why does it feel like we're moving? That's a really good question. And it's the same thing for the ISS. Because it's constant, this is a constant speed, 17,500 miles per hour all the time. You're not slowing down and you're not speeding up. It's going to feel the same to you. Just like it feels the same. Does anyone feel the Earth moving right now? If you did, I'd be scared. That could mean an earthquake. But yeah, we don't experience that because we need to accelerate or decelerate to feel that. Just like in a car, you only feel like you're really moving when you're slowing down or speeding up. So to give you an idea of how fast this is, though, at 17,500 miles per hour, you could travel from New York City to Los Angeles in less than 9 minutes. That's speedy, huh? All right. So the ISS going really fast. Tonight's International Space Station flyover. This came from a website called Heavens Above. It's one way to track satellites across the sky. They give you really nice maps to show you exactly where it's going to be. Now, this is a very high flyover. It's 52 degrees. So, we can use our measuring devices, right? If we did the 25 degree one, it'll just take 2. So 1, 2, up. You'll be at 50 degrees. That's about where this is going to fly over. And it's going to come out of the northwest at 8:33. So we're almost there. So I can't talk for too much longer because we got to head out there and check it out. But then a few minutes later, it's going to really start to taper off, and it'll disappear. And of course, the reason the space station is emitting any light at all is because of the sun. Remember, if we go back quickly here, you see those giant solar panels on this thing? The ISS is the size of a football field. With those solar panels, that's really what makes up a lot of the apparent size And all of those panels reflect a ton of sunlight. And that's where all that brightness is coming from. It's coming from the interior structures too, like the living modules and the main structure. But those panels contribute a lot to this. So this is the path it's going to follow. Northwest, and then it's going to stop about halfway across the sky. And it'll disappear because it'll move into shadow. Just like the Earth moves into shadow for nighttime, same thing will happen to the ISS. It will move into shadow. So that's what we're going to see in just a minute here. And I want to show this very quick. This will be the last slide. These are the astronauts on board right now on Expedition 65 of the ISS. 7 astronauts from the left. I'm going to do my best here. Piotr Dubrov, Shane Kimbrough, Megan MacArthur, Thomas Pesquit, Akihiko Hoshide, Oleg Novitsky, and Mark Vandehei, I think, is how it should go. And there's the breakdown. I won't run through the names again, but there's astronauts from NASA, the European Space Agency, JAXA, which is the Japanese Space Agency, and Roscosmos, the Russian Space Agency. So it's a really awesome collaborative endeavor with the ISS. And I invite you to wave to them. They might not see you, but let's wave to the astronauts when we go out. And I think we should do that now. So we're going to go on break outside. We're going to come back in here after to finish up. Oh, yes, thank you. So those on the live stream, we are going to take a brief break outside with the public to go check out the ISS. If you have clear skies where you are, and you're in roughly our area, you might be able to see it too. So go outside during our break. We'll be back in about 10 minutes to finish up this presentation. I'm still, yep. All right, those on the live stream, we are back. We're going to continue with the program in just another couple minutes here as people come on back into space science. And while I have a moment, don't forget you are welcome. I have the live chat up on my screen and here. You are welcome to post any questions you have for the Q&A session at the end of the show. Just going to take a quick peek. All right, it looks like we are ready to start here once again. So, it was great that we got to actually see it. It really was almost like a light. It was gradual, but once it got to that upper, one of the maximum points in the sky, it just started to dim, right? And almost turn off like a light. But don't worry, they're still there. And they'll be back around the Earth in another 90 minutes. Although not at that point. Rather, it won't be visible to us because it'll be too dark. The shadow's too far across our sky for them to show up again this evening. All right, so that is the ISS, and that was definitely one of the brighter ones I've seen recently. Okay. Next up, planets and solar system objects. So, this time of year, and when we go into what's called stellarium, I'll be able to show you where these things are specifically, but some of the objects that you can see in the evening and into the night, we have Venus, and Venus is right here. Now, Venus is interesting. At the very tail end of the fall, this is what Venus will look like. It's not a full Venus. It's a crescent, like you sometimes see with the moon. And that can happen with the inner planets, Venus and Mercury. If you were on Mars, you get crescent Earths every once in a while. We do not get the same effect looking outward, though. Occasionally, we'll get a gibbous Mars. But that's just because it's just close enough that in our orbit, sometimes we can look around towards the other side and get a look at the darker side of Mars in that moment. But otherwise, it's only the inner planets from our perspective on the surface of the Earth, Venus, and Mercury. And the only part that we can see in that image is just that thin crescent. Venus through a telescope, the phases are probably one of the coolest things you can see. Because Venus has such a thick atmosphere, we can't look to its surface. Its surface is very rocky. It's also very hot. We talked about in the other program how it's 880 degrees Fahrenheit at its surface. That's the hottest surface temperature of any planet in our solar system. So the phases are the coolest thing in a regular telescope. Now, if you can use scopes to peer in through to see the details in a different wavelength of light, then you can start to pick up some of that information. But Otherwise, through a regular visual scope, it's so cloudy. Always cloudy on Venus. All right, so there's Venus. You can see that. It is very bright, though. All those clouds mean it's super reflective, and it's, again, really close and also almost the same size as the Earth. So it shows up really nice and bright in the sky in the daytime as the sun is setting or the sun is rising, depending on which side. That's what you'll see. Next up is the moon. Now, a season lasts about 3 months, right? So, 3 months. So the moon, that means you basically get opportunities to see all phases for all those 3 months in a given season. So we'll go from full moon to new moon 3 times. And it's just under a month. It's like 28 days for the moon to do 1 orbit around the Earth. So that is the most dramatic object in the sky that you will see even shift its position in a given night. If you're looking up at the moon in the sky, you will notice, especially using that degree method we talked about, its position will change to the stars in the background. You will see that. And it's really noticeable looking at the phases day to day. Okay, we have the moon. We have Saturn. And this is kind of in order. Venus is first in the evening, then you get Saturn and Jupiter. So it's partially in order. The moon is the only one that's kind of out of sync here. Saturn sets in the sky after Venus. It's even pretty close to the horizon right now. It's getting there. And Saturn is, of course, famous for its ring system. All these pictures were taken at Kopernik, by the way. So this is our Saturn image, and you can see in this one, on the clearest of nights you can see this with your eye, but with cameras it becomes really easy to spot. You get the Cassini division, which is one of the big breaks in the rings of Saturn. And what's really cool too about Saturn right now is there is a shadow being projected on the rings from our perspective. So we're actually looking off to the side enough where we're seeing that sunlight and that Saturn block and project a shadow onto the rings themselves, and it sort of looks like a dark spot over on this side. So we'll see, maybe see that tonight. I think it's only going to get larger too as we orbit in the Earth's orbit. Okay, so the rings of Saturn, very nice. You'll also see some moons surrounding Saturn, like Titan. So you can see the moons through a telescope. To your eye, all of these objects just look like, except for the moon, all the planetary objects look like just a point of light in the sky, much like the ISS. But the moon, of course, is close and large enough that we can see some of its detail with just our eye. But again, it's only, when you hold your pinky out at arm's length, it's only the size of the tip of your pinky. It's even a little bit smaller than that. So even the closest object we have is still pretty small. So you really need a telescope to see these with detail. All right, then we have Jupiter. This image is pretty cool. You have the Great Red Spot right there. You see, that's the big hurricane storm system. At its largest size, it can be about 3 Earths across. That's huge. Imagine a hurricane like that. I mean, wouldn't even fit on our planet. So, largest planet in the solar system, Saturn is second. Do you see this dark spot? That dark spot is a shadow from this moon right here. You see the moon? That is Io projecting a shadow onto Jupiter that we caught with one of our telescope and camera systems. So for those in the stream, there's the shadow, and there's Io. Okay? So you can see storms, you can see these dark bands across the surface. Saturn is pretty consistent. There's a little bit of detail there and banding on the main planet. But with Jupiter, you have very intricate and detailed bandings. And if you could get right up close to it, like the Juno spacecraft is orbiting around Jupiter right now, there's some amazing pictures they've gotten of all of those cloud layers in the atmosphere of Jupiter. All right, then I put some asterisks next to these. Neptune, and I say Uranus. That's the Greek pronunciation. That's the one I use. Then these two are out right now in the sky. I think Uranus is starting to rise up in the east. They are not visible to the eye, though, and in a telescope, even in our largest scope at Kopernik, it can be a challenge to not only spot it, but to pick up enough detail that you can see it's a planet. The 20-inch is usually our best bet for that. The 14 can almost get there, and you'd see it as like almost like a weird ghostly disk, rather than a star that's flickering in the telescope. It would have a bluish color. Both of them would have a bluish color to them. So that's kind of neat. Otherwise, you're not going to get anywhere near the detail we're seeing here with Saturn and Jupiter. They are just so far away. Those weren't discovered until telescopes were invented. You needed something to spot them. They were not visible to the eye, like Jupiter and Saturn are. So those are your solar system objects, things that we can see, and again, most of them are visible to the naked eye. All right, let's talk the lunar eclipse coming up. So this is only a partial lunar eclipse, although it gets very close to a total. Now, when we talk eclipses, we have two types here in the Earth system. We can have the Earth's shadow projecting darkness, right, a shadow onto the moon. That's what this is, a lunar eclipse. Or we can have the moon come up in front of the sun, pass in front, and either do a partial eclipse there and only show some of the sun, or do a total eclipse and cover the entire disk of the sun, and you get what's the awesome experience. I have not seen it myself yet, but of the corona around the outside, the atmosphere of the sun glowing. And if you've seen total eclipse images of the sun, they're astounding. We did have some people from Kopernik go down to Tennessee back in 2017 for the total eclipse there. It did not happen here, though. It was only a partial eclipse in our New York area. The next one, though, is in 2024, and it will be about 97% coverage here. But I know, as much as I'd love to be at Kopernik, I know I'm going up to see totality up in the Rochester or northern New York region, because that's where you will get a total eclipse. And that's worth seeing, because even that 97%, that extra 3% of sun, you can't look at it with just your eye. It's still too bright. That's enough to cause damage, and it's just so close. It's such a short drive. You just got to go, right? So keep that in mind the next few years here. That eclipse is coming up, and will be well worth it. That is a more north to south, whereas the one in 2017 was west to east. Okay, so the lunar eclipse, though, again, is when we project our shadow onto the moon, when the Earth is shadowing the moon. And these can be partial or total, too. This one's going to be partial. So here's sort of the process when it starts. There's a penumbra, which is sort of, you really can't even notice the penumbra affecting the moon that much. It's just going to cause a slight dimming. It's just that out of focus edge shadow that you can get. And it's really not going to cause the moon to dim too much. This is the umbra, and that's the hard shadow of the Earth. And there's it covering a little bit more. And this is not like, your phases of the moon. This is a full moon. It only happens during a full moon. Just like total eclipses of the sun, solar eclipses only happen during new moon. This is a full moon, and you can see this is not like the phases. This is the actual shadow of the Earth. That roundness of this shadow is coming from our planet. And of course, you still have some of the sunlight almost totally exposing the other side, but eventually, during a total eclipse, you get to this point, where you can still make out detail because sunlight is wrapping around the atmosphere and diffusing through it and projecting back onto the moon. So there's sunlight, and that's where you get your blood moon. And that's what we see, where that reddish color. And the entire surface is covered by that umbra. So this was from the 2015 lunar eclipse. That happened in September. So this one is November 19th, starting at 1:02 a.m. So not a... You gotta stay up late for this one. And there's 5 stages to this, should say partial, to this partial lunar eclipse. You have the penumbral, the start of the penumbral, the start of the partial, then you get to your maximum eclipse, the end of the partial, and the end of the penumbral. So when you're in the partials here, that's where the umbra, the hard shadow, is affecting. I have a picture here to show you some of the differences. So here's our sun projecting light onto the Earth, and then we have the shadow of the Earth. The hard shadow is the umbra. That's actually going to cause the moon to dim and darken significantly. And then you have this diffuse shadow called the penumbra. That's really not going to affect it too much. So when it comes into this zone, if it's completely in the umbra, that's where you get total. We're going to just miss that. There's going to be a little edge there that will make it so it is a partial. But it'll still be pretty impressive, because when you're only having penumbral eclipses, those aren't that interesting, because it's still just almost a completely bright moon, just slightly dimmed and almost not noticeable to the eye. So this one's still going to be cool, and I think it'll be worth staying up late if you can. We'll look at this in Stellarium too, to see it play out. It's a little preview. Now this is an image I love. It was one of the astronomy pictures of the day that you can find on nasa.gov from a photographer, astronomer Lishan Wang. And it's a composition of the different phases of the eclipse. So you're looking at different images, and they're stacked in such a way, they're combined in such a way that you can see the entire shadow of the Earth. Do you see that complete sort of a half circle? You can almost you draw the line down here, and you're getting a complete shadow of the Earth through those different views of that eclipse. And again, you do get that nice. Now this one actually came pretty close to being just a partial, because again, if you complete this umbra shadow, it's very close to that edge, and that's why the bottom part is brighter than the top. This one's more in the umbra than the bottom, but it was still a full total eclipse. So that's the umbra of the Earth. Seeing that, I love the pictures that show you different perspectives that you otherwise can't see by observing it in that one instance. Okay. Now, getting into some deep sky objects here that we can spot, and I think some of you may have seen this outside when we went to look at the ISS. I think Mr. Desker pointed it out. The Milky Way. Here's how it looks with a camera at Kopernik. And this was summertime, I think 2020. And with your eye, it's definitely not this bright, but you can make out some of the detail that's in this image. And if you did see it outside, that was the better time to spot it, because the Milky Way is starting to set earlier and earlier as we head into the fall. The best time to see it is in the summertime at very convenient hours, but it sets pretty late here in the fall. We'll still see a good portion of it, but not the bright part. This is the core. Again, he pointed out, point it with my mouse here, so those on the stream can see it. This grouping of stars is the teapot. Here's the nozzle of the teapot, these 3 stars in a triangle. And you can almost think about it like you're dumping some tea out of the teapot, and the steam is rising up into the sky, and that's the Milky Way. So this points right into the core of our galaxy. And we can see that with just our eye. It's very important to note that this is really our the only way we can observe the Milky Way, because we've never flown out of our solar system, with the exception of Voyager 1 and 2, which it's kind of debatable if they're actually outside our solar system. So we've never gone outside the Milky Way to take a picture of it. This is our only view of it in the sky. And we have to sort of piece together what it looks like. We know it's a spiral galaxy, but we don't have a full image of it. We can only simulate one. Otherwise, this is what we have to work with. And it's pretty beautiful when you see it, even with just your eye, in dark skies, like here at Kopernik or Cherry Springs down in PA. That's another good place that's relatively close by. Okay, so that's the Milky Way. We'll check that out outside. The Andromeda Galaxy, our closest galaxy, the nearest neighbor galaxy to us. Here's an image. You may have seen this on our social media before. We've used it a couple times. But this is Kopernik here, the main building. There's a radio tower, and then next to it, can you see the little fuzz? This little fuzzy spot in the sky is the Andromeda Galaxy. Tonight, with no moon in the way, we'll be able to spot that with just your eye. It's pretty high up, and you can see an entire separate galaxy from our own, the Milky Way, with just your eye picking up that light. I think that's fascinating, thinking about how many worlds, how many planetary systems are in there, stars, billions and billions of stars, all with just your eye picking up that light. So we'll see that. The Andromeda Galaxy, we can take a look at it up close maybe in Stellarium 2. Then we have nebulae, like the Dumbbell Nebula. There's also the Ring Nebula, is a very similar one to this. Here's the Dumbbell, though. Can you sort of see why it's called the Dumbbell? And this is a planetary nebula, and that's because when you look at it in a scope with your eye, it sort of takes on the shape of like a disk of a planet, similar to what I was talking about with Neptune or Uranus. This one is a lot more details brought out when you take a long exposure with a camera and you start to make out this is definitely not a planet. It's much, much bigger than a planet if you were right up close to it. Because here is the star at the center, the little white dwarf star that exists after it started expanding, and blowing off its outer layers. This gives you an idea of what will happen to our sun in about 5 billion years. So it will eventually just start expanding its layers out, grow bigger and bigger, and then it will just diffuse. All those outer layers will diffuse into what you see there. And it leaves behind a pretty beautiful remnant of what's effectively a dead star. The star is still burning for the most part, but it's not putting out nearly as much energy as it once did. And it's sort of like time travel. We're looking at what could happen to our sun in about 5 billion years. Very similar star to our own once existed in that area of space. Alright, so the Dumbbell Nebula, you can see it with your eye, but a camera picks up a lot more detail. That's the case with a lot of these objects, these deep sky ones. Here's the one that gets really cool through telescopes. The Orion Nebula. And this will continue to rise earlier as we head towards winter. In fact, once you start seeing this in the summertime, you know summer's coming to a close. Or you've stayed up way too late. So here's the Orion Nebula. This can be found in just below Orion's belt in the constellation of Orion. And unlike the planetary nebula that's remnant of a dead star, this is a stellar factory. This is where stars are born. And it's almost like a funnel shape. So you can think of these stars all towards the center. In fact, there's a really nice grouping that's overexposed in this image, so you can't see them. But there's a really nice grouping right in the middle, and the stars are just almost like flowing out. They're spewing out of this funnel in space. And it's a very bright object. You can see a good portion of the cloud, the stellar cloud, with just your eye. It looks more green to your eye. This is true color by a camera, though. I didn't do anything special to my camera or filter it. It was just a long exposure, so it was collecting light, a lot of light over time, and this is what you get from it, sort of a purple-blue. And that is, again, sort of where stars are born, at least in that region of space. We came from a nebula much like that one, or at least our sun did. And this is really where things start for solar systems. Just one of the many that are out there, though. Orion Nebula is not the only one. Okay. Let's talk about tools you can use. This will be the last portion of our show here tonight. and then we will go and observe the sky for real. So, first one is Stellarium. Stellarium is free software. It's like a planetarium at home. We have like our portable planetarium, we inflate it, and we have a projector and computer system, and it will show us the sky in this big dome. We'll project a hemispherical view of the sky. And this is a 2D version of that. So putting it on a regular screen at home, and I can show you that here. So here it is. Let me reset it. And you can see the constellations on there right now. You can put the artwork on, or you can turn it off. Just put the labels on. So you can spot any constellations you're looking for. There's Hercules, and the Little Dipper, as well as the Big Dipper. Some of you saw the Big Dipper outside, right above the horizon there. And if we want, we can even go hunting for deep sky objects like the Andromeda Galaxy. So here's the constellation Andromeda. And we can hopefully highlight somewhere around here. There we go. The Andromeda Galaxy. There it is. If you took a long exposure of Andromeda, that's the galaxy you'd end up with. And a lot of the deep sky objects in here have images like this. So real images taken from a camera and a telescope. So that's what Andromeda looks like. To you in the sky, this is actually very accurate to what you'd see with your eye, sort of just like a little fuzzy spot. That's what we'll try and compare that to the real sky when we go out there. Okay, you can also do things like the planets. So here, this is a live sky right now too. We're at our 42 degree latitude and our negative 76 longitude. So what I'm going to do is add something called the ecliptic. The ecliptic represents the plane. See that go? Do we have to hit all three of these? There we go. The plane of our solar system. So when solar systems form, they often form in a protoplanetary disk. So you have your sun, your star at the center, and then you have this disk of material surrounding it, and that's where all the planets form. And that's why, more or less, all these objects fall along the same line in the sky. At least the main planets. And the moon is in this way too. The Kuiper Belt objects is where things get a little dicey. Like Pluto comes in at an angle in the plane rather than follow the plane. But here we have Saturn and Jupiter right along this nice line. The sun follows this line too. And if you click on an object, you press the space bar, you can zoom in with the scroll wheel, and just like a telescope, there's Saturn. And you see that shadow I was talking about? It simulates that too. It shows you what you'd see in a telescope. So look for that shadow if we see Saturn tonight. Same with Jupiter. Click Jupiter. That's where it is in the sky right now. Both of these are almost due south. Saturn's almost exactly due south. Here's Jupiter. And you can see the moons of Jupiter too. You'll see those in a telescope.
Jupiter right now on the 6-inch, and you can see those equatorial bands.
Oh, yeah. Yes, yeah. So, like in that picture before, you had, and the red spots coming right around here too, you have these equatorial sort of reddish tan bands across, close to the equator. The equator is right here, so up in the north and south of it. And those will come very clearly. On the best nights, you can even make out some distinctions here in these cloud layers above and below. But those two big ones are really easy to spot. So look for that detail on the surface. And if the red spot does come around as the night goes on, you might see that too. So you can look at planets. Like I said, here is Uranus, and very dim, but you can zoom in more than you could with a telescope, and you can see the ring system of the planet. So you can do more than even telescopes can do here on Earth. Or at least, the smaller scopes. And then you can go exploring some of the constellations, and we'll look at the Summer Triangle tonight. The Summer Triangle is starting to move westward because it rises eastward in the summer, in June, you'll start to see it rising up in the sky in the east. Now we're in fall, so it's going to be setting in the west. And it'll happen earlier and earlier as the fall goes on. So the summer triangle is Deneb, Vega, and Altair, 3 bright stars. Remember we talked about how Vega is a very bright star, right at that 0 brightness. So look for those 3. And I won't do too much more touring of constellations on here because we have a really nice sky to look at out there for those. But I really recommend downloading this software. I think I brought the page up. Yes, I did. Again, it is free. You can download it for any platform. You can even just run a web version, a web-based version. You don't have to download anything in this way, or if you have a Chromebook, it works great for that. And you can set your location, and it operates the same way. There's not as much intricate details you can bring up, but you can do the constellations, you can look for planets, you can zoom in, you can look for some deep sky objects. It's pretty full-featured for the basic stuff you'd want to do. Now, I might return to Stellarium towards the end again, but go to stellarium.org if you want to try the web version or you want to download it. Alright, so there's Stellarium. You do have some other options, though. And the tool you're most likely to have on you when you're out observing the sky is not a laptop, it's not a desktop computer. It's your smartphone. And there are a bunch of apps that you can download there. This only covers a very small portion of what's available there. And there's Starwalk, there's Sky Guide, and these are the ones I tend to use. I don't prefer anything like that. It's not a sponsor or anything, but these are the ones I like to use. And there's free versions, there's paid versions that give you more objects. You can value that as you may. And then there's a really expensive one called Sky Safari. And if you have a telescope at home that is computerized, this is the one you want because this lets you operate your scope in addition to look for these things in the sky. So that one's really handy for the professional experience. But these are great and they basically do the same thing as Stellarium, but it's on your phone. And more than that, especially as smartphone sensors become more sensitive, they're able to pick up more stars in a live camera feed. And a lot of these apps have something called like Sky Sync, where you hold your phone up in the sky. It already tries to figure out where it is based on your compass, but you can perfectly align things by using your camera. And as long as you can see the objects coming through, you can line up the sky, and you know when you're hovering it over, you know exactly where those objects are as you look at them through your smartphone. So those are great. And of course, this sort of goes hand in hand, but there's more that you can even do with your smartphone now as they become, the cameras become better. And you can take pictures. So there's a picture of the moon taken on a smartphone, and there's a picture of the Milky Way. These were just taken last week, and by no means is this the best picture of the moon that you can get. Obviously, you'd want to use a telescope to get clearer detail, but the best camera is the one you have on you. And if a smartphone's all you have, look at what you can do now. Compared to even just 5 years ago, this was not possible. So keep that in mind when you're taking pictures of the sky. A lot of smartphones have something called night mode. You wouldn't want to do that for the moon, it's too bright. But for the Milky Way, you can take pictures of that object. You can see, it's not as nice as the other image, but you can see it, and you can see the stars around it, and you can see Sagittarius down here. So it's worth a try. Worth a try using your phone to take those pictures. And I think that wraps it up. Yeah. So we have, and I'm glad this is actually true. So that's more or less a greeting more often than not, but this is true too tonight. So we're going to be able to observe some things in the night sky. I really recommend that you go and download those applications, even if it's just Stellarium on your computer at home. But try the smartphone ones too. And otherwise, I'm happy to do some question and answers. If you have any questions about what we talked about tonight, feel free to just raise your hand and I'll answer those. I'll also look at the live chat on the stream and see if anything came through. Are there any questions about what we talked about during this show? Oh no, I haven't yet. I did in the 3D universe, but yeah, you're not allowed to go anywhere tonight until you see the lunar sample we got from NASA. That is from Apollo 17, and it was picked up by astronaut Schmidt on the moon. It's just it's just one sample of the larger rock that they picked up and brought home. So definitely check that out. I'm not sure when do we lose that rock?
Sometime in December.
In December. Okay, so it's only here for a limited amount of time, so make sure you get to see it. Yes, exactly. Yep. All right, so let me look at the chat quick to see if there's any questions. Nope, nothing in there, so I think we will.
Mark, can I get you to go to the 6th? Yeah. Right, because we've got Jupiter in the 6th, and so take a look at that, see if you can discern those equatorial bands. And I do have Saturn in the 14th, so especially if this is your first time here, you're going to go through those double doors on the other side of the lobby, to the left, and then down this little hallway, and then to the right is another building. And you go out, there's a little bit of a ramp up. On the left is what we call our 6-inch scope after Jupiter. Jupiter's on the left, Saturn will be on the right.
All right. Thanks for joining us on the presentation. We'll see you outside. Oh, it looks like we do have a question here.
Jeremy, I'm going to go into the 14th for now. And then when you're available, you can slide in Mark's on
Sure.
the 6th.
Yep, will do. Yes, we do have a question here on the live stream. So, do other planets have moons the right size for a solar eclipse? If I remember correctly, we are the only one that has the right sized moon to get a total eclipse with the corona showing and everything. But eclipses certainly happen on other planets as well. In fact, the Curiosity rover on Mars recorded a eclipse event happen for both Phobos and Deimos. They saw those pass over. So they do happen, but we sort of have the unique case where the moon is just the right size to fill out the sun every once in a while. Doesn't happen all the time. Sometimes we just get partial, like an annular eclipse, but that can happen. Are there any other questions in the live chat? I see everyone, at least that might be close by, they have some clear skies. That's great to see or hear about. That's great to hear, Lauren. That is exactly what we want to do here at Kopernik, is inspire the next generation to explore the stars. Very good. All right, with that said, I have to go out and help with the observing session that's happening outside our building now in the telescopes. And just so those that are nearby are aware, we are open every Friday now, starting at 7 p.m. for our Family STEM Hour, after which we do our 8 o'clock presentation. Let's try that maybe. Okay, my mic cut out, unfortunately. I think the battery died. So
Yes, but anyways, we're open every Friday night, so if you can make the trip, feel free to visit us. Otherwise, we are going to be doing some more observing live streams, and we just announced that we're looking into doing a more regular event stream, like a webcast. We'll see if we can get that going. That won't rely on clear skies, which is nice. So keep that in mind too. Whoa, from 3,000 miles away? That's crazy. That's like almost a half Earth diameter across. Well, I'm glad I was able to answer that for you. But yes, we'll do more observing streams too, and I want to try and do a lunar eclipse stream on the one we talked about during today's presentation. It is going to be at 1 a.m., but the nice part is you can always watch afterwards, right? So you don't have to be up with me to do the live stream, but I'm hoping I'll be able to do that one at Kopernik, and I can talk to people that do tune in on that late night lunar eclipse. All right, well, with that said, I'm going to wrap up the stream this evening. Thank you for tuning in, and we will see you next.